Start talking? All right. Hello, everybody. Can you hear me?
Yeah.
All right. My name is Brandon Wilson. I'm going to be talking about intercepting and or manipulating USB traffic for both good and evil. Show of hands, who's here for the evil part? Who's here for the good part? Who here thinks by evil I meant attack and by good I meant defense? All right. So we know who's who now. I'm going to go ahead and apologize in advance. I was in a mad rush to finish these slides, and I'm a terrible public speaker, so I'm going to pretty much be reading the slides. Sorry about that. So you'll have to bear with me, but we'll get through it. All right. So to talk about USB, you first have to know what that communication looks like. Who here has ever written code that interacts with a USB peripheral or pretends to be one, like libUSB or Linux USB gadget drivers, Arduinos, Teensies, keyboards, gamepads, anything like that? Couple? All right. Or for you guys, you hopefully already know what I'm about to go over then. Crash course on USB. At the top of the USB chain is the USB host controller, which is capable of talking to up to 127 different devices, each having a unique address assigned to it by the host. And all traffic is broadcast from the host to all the devices downstream, and each device is trusted to only communicate on the address given to it by its host. And note that a hub does count as one of the 127 devices. And as I said, each device has a unique address and is capable of communication on up to 16 different channels or endpoints. And these endpoints have a number of features associated with them. A number, like a unique number that identifies it, a direction, so either incoming or outgoing, but not both, and then a type. And that type can either be control, bulk, interrupt, or isochronous. Now, I kind of lie, control endpoints actually are bidirectional. They're not only required, they are also required, and every device must have one and only one, since that's what all standard USB requests go on, like setting the device's address, setting device features, etc. Bulk endpoints are used to transmit large bursts of information, and they have the lowest priority on the bus. And interrupt endpoints are low latency, so they have the highest priority on the bus, and they are used to transmit small chunks of data like keyboard key presses. And isochronous, that's how I say it. Endpoints are used to transmit large amounts of data as well, but unlike the other endpoint types, there is no error checking involved, so they are for when you want to transmit data as fast as possible, even if some of it ends up corrupted on the other end, like with headset audio. And it may surprise you to know that the host is responsible for all transfers, even the incoming ones. So if a device wants to send data to the host, it has to buffer the request and wait for the host to ask for it, if it ever does. So when I say interrupt endpoints have the highest priority on the bus, that means it gets pulled more often and before all the others by the host. So what happens when you plug in a USB device? Well, the host or a connected hub, whatever you plugged it into, detects a new device has been connected. The host then enables power to that device at its location by the host controller driver, and then that device is expected to start at the default address, which is address 0. And since the host just enabled power to the port, it believes it can communicate with the device on address 0, assuming that nothing else would be on address 0 anymore. And so it allocates a new address and tells the device what its new address is, for 1, 2, 3, 4, 5. And the host then assumes that further communication will happen on that new address. And it requests a device descriptor on that required control endpoint, and then a configuration descriptor. And then that descriptor contains information about all the device's interfaces and endpoints for each one. And at that point, the host can load drivers for each interface, which contain the logic for knowing what each device is, what endpoints it has, and so on. So communication can then start. So having said all that, what is this bad USB thing we keep hearing about? Well, it's just the device lying to the host about what it really is. So, it's about reprogramming a USB device's firmware to behave differently than originally intended. And, it's hardly an exploit or anything. It's just changing what interface and endpoints and so on the device claims that it has and what traffic it sends. In that specific case, where the term bad USB came from, it's about reprogramming the firmware stored on a USB flash drive. A lot of people didn't realize this, but a flash drive is kind of a little mini computer. It has a CPU, RAM, some code to boot off of, and most importantly, additional circuitry for communicating over USB and the NAND flash memory that's inside that drive. So when a PC requests data from the drive goes through a lot of complicated steps to find the physical location of the data on the NAND chip before returning it back to the PC. And naturally, since it's complicated, there are firmware updates for it that become necessary from time to time as NAND and USB controller bugs are identified and fixed. And the big problem here is that these firmware updates are typically not cryptographically signed, so we are free to change them to do whatever we want, flash it back to the device, and then we own it. So, for example, instead of a flash drive's firmware choosing to expose a mass storage interface, which is what it would normally do, it instead exposes a keyboard interface with an incoming interrupt endpoint and then quote-unquote types out some malicious scripts as quickly as it can before the user knows what happened. So the problem could be even worse than that. What if the device starts violating the USB specification in strange and unexpected ways? So like imagine if it suddenly changed its own address and started listening to traffic that didn't belong to it, or spoofed traffic as though it came from another attached device. So for example, way back in 2010, the first exploit for unsigned code execution on the PlayStation 3 came out, and that relied, it's called PS Jailbreak, and that relied on a memory allocation issue when connecting and disconnecting many devices on an attached USB hub in rapid succession. So after that, cell phones, USB development boards, TI graphing calculators, everything with a USB controller that allowed changing its own device address could trigger that exploit by pretending to be a hub, and then virtually attaching devices by claiming new devices are attached, and then switching to address 0 to briefly pretend to be that device before going back to the hub address and then virtually attaching another one and another and another and another. The latest Chromecast root, it's called hubcap, and it also does something very similar to this with hubs and messing with the device address. So no matter what we do or don't do with it, it's simply too dangerous to leave it attached to the bus. So what are our defenses against this kind of thing? Well, we can disconnect 2 of the 4 USB lines, the 2 responsible for data transfer, data plus and data minus, like what the so-called USB condom does. But if you do that, you can't communicate with the device. You can only power it, so that's kind of useless. You could use a cheap Linux board like the BeagleBone Black, something that can both simulate a USB peripheral and has a USB host controller for attaching other devices. So we could simulate the USB peripheral and only relay the communication we expect between the host and the peripheral. So, if we want to hook up a flash drive and it suddenly starts sending me keyboard key presses, I'm just going to ignore it and not let that make its way back to the PC. The problem with that is Linux is a complex OS with limited low-level access, just like the hosts, so it can be compromised as well, arguably just as easily as Windows or anything else, or a PC. So the third one, I've seen discussion out there about making a totally custom board with code that only relays the traffic it understands and expects, which is actually not a bad idea, but that requires manufacturing a custom PCB and soldering components yourself or waiting on someone else to assemble it for you, which people don't necessarily want to do. So the project I came up with as a solution to this problem is called Vicar, which consists of an Arduino compatible board and the USB host shield for the Arduino. And if you ever messed with the Arduino before, this thing may look familiar to you. It's used all over the place when an Arduino board needs to communicate with a USB peripheral, like a Bluetooth adapter, flash drive, and so on. It contains a Maxim Max 3421E USB controller chip for communicating with any USB peripheral, including a flash drive that you might not trust. So instead of your PC having to talk to the untrustworthy device directly, it can tell the Arduino to do everything on your behalf, which isolates you from anything tricky the device might try to do. It is possible to buy this shield with the headers actually already installed, so you can simply slap it onto an Arduino and you're done. You don't have to solder or anything, if that's not your thing. The Vicar code flashed to the Arduino exposes an API to the host that allows low-level control of anything attached to the USB host shield's USB port. So essentially, you are becoming a USB host controller driver instead of having to trust the one from your OS. That means it's up to you to handle enumeration, such as detecting a new device is there, making up a new non-zero address for it, sending the set address control request to let the device know, and then switching to that address, communicating on that. It might sound kind of tedious, and it is, but it gives you the ability to handle weird scenarios, such as a peripheral suddenly switching to another address without your say-so. It also gives you the ability to handle multiple devices. So, if you plug a hub into the USB host shield, then it also becomes your responsibility, if you choose, to respond to any new device connected on port events from the hub. So it's not limited to a single device. You can do anything you want to over USB through this thing. So there are a lot of different ways to use and interact with this Vicar device. When you first plug it in, it defaults to a human interface device, or HID. And since there is a class driver for that on any modern OS, you don't need to install a separate driver first. The OS will automatically figure out what to do with it. It goes to this interface by default because that's the safest one you'll be guaranteed to still be able to talk to, no matter what restrictions might be in effect on the computer you're plugging this into. Unfortunately, however, HID is not that great for sending variable length command packets, only sending a fixed data report each time because it's intended to send back structured report data like key presses. So in this mode, I enable all packets, or I made all packets 128 bytes, which can be slow and wasteful because every time you want to send a command to tell it to do something, you're sending 128 bytes over the wire. So that brings us to the second option, a custom vendor-defined interface, which would allow us to send anything we want. Normally, you would need to supply a driver to communicate with an interface like this, especially in Windows, but the Vicar code supports the Microsoft WinUSB OS descriptors, which essentially means Windows 7 and up, will automatically detect it and install a WinUSB device driver for that interface. And then on other OSs, you can always just use libUSB. It's much simpler. So, first demo. So imagine a scenario where you're in a locked-down Windows environment where you're prevented from being able to mount USB mass storage devices. So then you ask, well, what kind of device can we connect? Well, since we have to be able to, type, obviously, we know we can still connect USB human interface devices for plugging in a keyboard, which means that theoretically we can still communicate with Vicar as well, even without administrator privileges, as long as we do it through that HID interface. So since we can communicate with Vicar, that means we can also communicate with any device we plug into the USB host shield, like a flash drive. So we can write some code on the PC to issue mass storage read sector and write sector commands to the device, and we'll be able to read or write any data that we want. And that's great and all, but to make it useful, we need some way to get to actual files, not just the sectors. Nobody cares about the sectors. Then that's where the .NET disk utils library comes in. And that library has support for reading and manipulating disk images in a lot of different formats, including FAT32 and NTFS, which is what you're most likely to see on a flash drive. So by creating a .NET implementation of that Vicar API and combining it with the disk utils library, we can put together a simple shell for browsing directory contents and reading files from or writing files to a USB flash drive without the ability to actually use a flash drive. And so I will try to show that to you. Let's see. Nothing there. It's a little better. Well, maybe not. Well, it's not important. All right. Okay, so that .NET code that I wrote for communicating with that Vicar device supports both the HID interface and the custom interface. And so it looks for both. So when you first plug it in, when you first start this, it looks for either one. It found the HID one, it detected it, and it's waiting for a device to be attached. And here's the device, by the way. I didn't use an Arduino. I used a Teensy 2.0 device, a teeny tiny version of the USB host shield. And then it's got a flash drive plugged into that. So it detects it, waits for it to become attached. It is attached, and then it started sending mass storage commands. So now we're at that simple shell I was talking about. So we can look at the files on there, and you can see there's one directory and one file. And if you can get it, actually let me get out of this and turn on verbose mode. Once I unplug that. Yeah, so those are all the mass storage commands that are going across. Now this is what this is what's actually going across the wire. So because we're using the HIT interface, it has to transfer that much data all at once. So you're seeing a lot more than you normally would be, a whole bunch of zeros. But those are the commands that are going back and forth. So I'm going to turn that off because it's really annoying. Again, forgot to unplug. Okay. So we'll get that test file. File retrieved. This is that directory. Oh. And then there's the file. And you can also go the other way. You can write files there. You can write files there. So we will put another text file I have here. And file written. Now it doesn't actually send the commands to the device until I tell it to. So there's a flush command I put in here. So if you run flush, it will actually write the sectors to the device. So you can mount it read. It's effectively you're mounting it read only. Then only if you want to persist the data, then you send this flush command. Okay, so it's flush. We'll disconnect. And we'll plug in the drive directly. Eventually. Well, let's not wait around on Windows. We'll just move on. All right. Just trust me, it's there. All right, so that's great and all, but I don't want to have to re-implement the entire mass storage protocol and the code to handle the file system stored on there. It would be nice if we could get the host OS to handle all that stuff for us. So for specific scenarios such as mass storage devices, there is an option. We can make the Arduino expose an additional mass storage interface and push any mass storage traffic from the device straight to that interface. That way the PC just sees another drive and it can do all the work for us. So you can see I've got two interfaces there, a keyboard one and then a mass storage one. It's just a couple of dummy interfaces that the PC will install drivers for as soon as you plug in the Vicar device for the first time. Now these don't actually do anything until you tell Vicar to start forwarding traffic between the attached peripheral and the host OS. So the keyboard interface doesn't send any key presses, and the mass storage interface claims no media is inserted. But once you do send the command to start forwarding data, then the PC will suddenly begin receiving the real mass storage commands from the responses from the peripheral. And now, instead of no media being inserted, it sees the drive's data and starts mounting drive letters and so on and so forth. And any attempt by the malicious device to claim it's something else will just be ignored because Vicar's the one that's talking to it. Only mass storage like data that I've verified, that the device can verify, will get sent back to the PC. So now that the Vicar device is firmly entrenched between the host and the attached flash drive, we can choose to send what packets to send and what packets not to send. And that's exactly what a USB write blocker does. We forward everything except the one specific command, which is the write sector command. Now, I was going to show you a demo of this, but it occurred to me there's no point in showing you something that doesn't work. See, it doesn't work. There's no point in that, so we're not going to do that. I will mention, though, that it's not just about ignoring certain packets. We could handle it ourselves and respond that it succeeded, even though it really didn't, so the host would never know. So it's not just ignoring things. You can do whatever it is you want to do. So what else can we do? Well, we can communicate with any device that your host OS's USB stack normally just isn't capable of. So, for example, a while back, FTDI released an update through Windows Update that would brick counterfeit serial devices by updating the device's USB product ID to 0, which gets returned to the PC during enumeration in the device descriptor. Now, that by itself wouldn't actually brick it, so to speak, but it would prevent Windows from seeing it because Windows just assumes that you'd never have a product ID of 0, so it just doesn't bother with it. So if Windows can't enumerate it, you can't run anything that would talk to it and fix it to change the product ID back to what it was. But with Vicar, you can choose to ignore whatever weird descriptors the device might return, or even not bother requesting them, and just send whatever commands you need to send to change it back to a non-zero value. So hopefully, as people get more inventive with screwing up USB, we'll be able to write code that counters it. So wrapping up, kind of sweat. So wrapping up, this is definitely a complicated project to try to accomplish within the few weeks I gave myself to work on it. I had to completely rewrite the USB host shield library for the teensy so that I could create the protocol and the interface for manipulating USB at a fairly low level from a PC, working from the ground up and trying to build a relationship between the USB host shield's chip and a libUSB-like interface on the PC. Also, relaying traffic like this is really slow, so to accommodate that, I modified that .NET diskutils library to add a caching layer, so it would only read sectors from the drive only as it needed them to interpret the FAT32 partition, and come up with a way to communicate overhead and send large chunks of data as quickly as possible. Also, as I mentioned before, the HID protocol is limited. Inert endpoints used by HID may be low latency, but it's not good for transmitting a lot of sector data between a PC and a drive. So the only way to transmit large chunks of data at once on a HID device is through that control endpoint. So I created a second HID interface with an extremely large HID report, which is 4 kilobytes, which is the maximum that Windows and other OSs will allow, and reserved that just for transmitting a lot of endpoint data, back and forth. So it's pretty clunky, but it's kind of a workaround, but it does work. Also, not all our Arduinos are created equal. To create the Vicar interface, we need to be able to customize the USB connection between it and the PC. And most Arduinos don't do that. They just expose a USB to serial interface for serial debug logging and nothing else. But some variants, like the Arduino Uno, are capable of it because they use a dedicated AVR for handling the USB communication, one which has rewritable firmware. Fortunately, though, I didn't have time to work on that, so all this only works on the Teensy 2.0 device at the moment. And the pins don't line up between the Teensy and the USB host shield, so a little bit of soldering wires is required, but just wires. That's something most people can handle. And finally, it's not news to anyone that knows me, but I am, in fact, insane. I can't say this project worked out as well as I'd hoped it would, but I did essentially get it working, and I still maintain there's a whole lot of value in having a device that shifts the responsibility of communicating with USB at a low level to the PC instead of embedding it being embedded in some device's firmware and just hoping that it does what you want or need it to do. So hopefully this talk and this code I'm putting out there gets a little discussion going amongst us, and if nothing else, it was definitely a learning experience for me. I don't have the Vicar code up at the GitHub link that you see there at the second, but I will shortly. Here's some links if you want to buy or use any of this stuff or get in contact with me. So thanks for your time.